Okay, Lewis diagrams of molecular compounds. Molecular compounds, as the title suggests, are made of molecules. So just to refresh, that molecules are a group of atoms or a cluster of atoms bonded together. Now, you will find that those are covalent bonds, the electronegativity differences being less than 1.7. So when you look at the formula of a molecular compound, you'll quickly recognize it because the elements that are present are nonmetals only. So remember, hydrogen, way over there on the left side, far left side of the periodic table, is actually a nonmetal, which is usually, we say on the left side are the metals and the nonmetals on the right side of the staircase, but hydrogen is a nonmetal. So let's understand in detail then that sharing of electrons. So if we have two hydrogen atoms, I'll use a dot to represent one valence electron for one hydrogen, the one on the left, and an X to represent that on the right. In order for these atoms to become stable, hydrogen needs to either lose or gain electrons to fill that first shell, or another option is share. And really, we have to compare the ability of each of these atoms to attract electrons to themselves. Because the electronegativity of both hydrogens is going to be the same, essentially in the tug of war for these electrons, they're going to end up sharing. And in doing so, they form what we call a single covalent bond. So this single line here between the two H's represents that shared pair. So this is a single covalent bond. Now we can look at Cl2. So Lewis diagram of a chlorine atom, group 17, 7 valence electrons. We have a second chlorine atom, I can tell because of that subscript there, and I'll use X's to represent the 7 valence electrons here. So we can see with 7 valence electrons, the chlorine is almost stable. Now, being that these are the atoms of the same element, they have equal electronegativity, so the difference will be 0. They're going to equally share the electron pair. And so we have, that didn't look very good, and so we have the equal sharing of those two electrons. So I'll represent that single covalent bond with a straight line and show the valence electrons that are not involved in bonding as lone pairs. So this here, this is a lone pair of electrons. So they're essentially non-bonding valence electrons. Remember, the Lewis symbols only show the valence electrons. And so we'll have the bonded pair shown, indicated by the line right here, and lone pairs. So there are 3 lone pairs here and 1 bonded, 3 lone pairs here and 1 bonded. Okay, now focus for a moment on the valence electrons surrounding this chlorine atom on the right. Do you count 8 electrons? Because we are looking for that octet rule. Hopefully you see 2, 4, 6, and remember this line, including the shared electron, right, is 2 electrons. So 2, 4, 6, 8, there's 8 electrons there. Now, if we were to go back to the left side and look at the left side, perhaps I could use, there, we've erased it there. So now look at these valence electrons around this chlorine. Do you also see the 8 electrons? 2, 4, 6, 8. Yes, so each atom here is stable. And so we've made each atom stable. The diagram is finished. Now checking over on hydrogen here, the hydrogen on the left really just has the shared pair. That counts as 2 electrons, which is enough to make that stable. The hydrogen atom on the right has the 2 electrons, also the shared pair, and so that makes that hydrogen stable. Okay, let's have a look at methane, molecule of methane, CH4. So we have carbon in the middle with 4 valence electrons, and then we have 4 hydrogens surrounding. So perhaps you can anticipate the sharing of electrons that's going to happen here in order to make a molecule of methane. And so we'll have carbon singly bonded to each hydrogen. Now look for stability. So look around the carbon, counting any shared and lone pairs on the carbon. Do we have the octet rule satisfied? 2, 4, 6, 8. Yes, we do. Check each hydrogen. When you're looking at the hydrogen, right, each hydrogen is going to have the shared pair, and that'll count as 2 electrons. So each hydrogen is stable, the carbon is stable, and we have 4 single covalent bonds. Now, just to be clear about the terminology up here, molecules. This is a molecule, right, which is a cluster of atoms that are covalently bonded. So the atoms, right, are the hydrogen here and the carbon in there and so on. So there are 5 atoms here. They are covalently bonded because the electronegativity difference between carbon and hydrogen is less than 1.7. So you don't see any ions here. We're showing covalent bonds in these diagrams. Okay, moving on. See if you can come up with a diagram yourself for water by looking at the 2 hydrogens and 1 oxygen that you have. I'll give you the suggestion to put oxygen in the middle and hydrogen on either side. So check out the group number, the number of valence electrons, and see if you can put the puzzle together to ensure that each atom in this molecule is stable. Okay, so perhaps you laid out the 6 electrons like this, setting up a single shared pair on the left and a single shared pair on the right. And in doing so, that will set up 2 single bonds in this molecule. So you'll see that there are 2 single bonds and 2 lone pairs around the oxygen, for a total of 2, 4, 6, 8 electrons around the oxygen. And each hydrogen is stable with the 2 shared electrons. Okay, now what about O2? So oxygen gas. Pause the video and see if you can come up with how to arrange the valence electrons so that each oxygen is stable through the sharing of electrons. Okay, and so you'll see that if we set up 2 electrons from each oxygen in between the 2 and set up a sharing here, that will then make for 8 electrons in total around each oxygen. So looking at this oxygen on the left, we have 2, 4, and then 6, 8. And looking at the oxygen on the right, 2, 4, 6, 8. So this molecule now contains a double covalent bond. Okay, now you can try N2 as the last example here, and then we'll move on. So go ahead and draw the diagram for N2. Okay, so I'm showing N2 here, and you can see that there's a triple covalent bond formed. Each nitrogen in group 15 has 5 valence electrons, so it will need 3 more electrons to become stable. And so we've set up the sharing for 3 other electrons now between the nitrogen atoms. And so each nitrogen becomes stable, according to the octet rule, with 2, 4, 6, 8 electrons. And looking at this nitrogen, 2, 4, 6, 8 electrons. Okay, so this is very much a trial and error method where we are using the number of valence electrons that we know and essentially fitting these pieces of the puzzle together. So that is difficult when molecules become more complex. And so I taught that initially just so that you would have a really good understanding of the sharing of electrons and the octet rule. But now what I'm going to do is construct a series of steps that we will follow to do these simpler molecules as well as more complicated ones. So take a moment and jot down the steps, and then we'll go through some examples together. Okay, so here are the steps. You'll see in the first step we count the total number of valence electrons. Remember that we look at the group number for the number of valence electrons. Second digit for double-digit group numbers. We will be drawing Lewis diagrams of polyatomic ions. If the ion has a negative charge, we'll be adding electrons to our count, and for cations, we'll be subtracting electrons. Okay, second step will be to place the atoms on the page, and this, experience will help, but definitely you can follow the rule that the central atom is the one with the highest combining capacity. So what I mean by that is look at the atoms involved in bonding in the molecule, and whichever atom needs the most electrons to be stable will be the central atom. Hydrogen will always be on the outside, so always a perimeter or outside atom, and halogens needing to make one bond are usually an outside atom. I will do some examples with oxyanions, and you'll see if hydrogen's involved that we'll definitely place it outside of an oxygen. So I'll show you what that looks like at the end of the examples. After we've counted the electrons, the valence electrons, and placed the atoms on the page, we'll place lines to represent the single covalent bonds between atoms, counting by twos as we do so. 2 electrons per line. Then we'll place remaining electrons as lone pairs on the outside atoms first, and then if there's any remaining, we'll move to the inside or central atoms. Always check for stability following the octet rule, so typically we're looking for 8 electrons. And if all the atoms are stable at that point, you'll be finished. But if the central atom is not stable, we're going to reposition lone pairs from a stable atom to form multiple bonds. So that's where you'll see double or possibly even triple bonds forming. If we've drawn the Lewis structure of an ion, then we're going to use square brackets and write the charge outside as a final step. Okay, there are a few exceptions to the octet rules, so I have just indicated these below, right here. So you'll know that hydrogen is stable with 2 electrons, beryllium with 4, boron with 6, and you will on occasion, more commonly in our next course in grade 12, but you will see the central atom perhaps need to hold 10 or even 12 electrons, and that's okay as long as the central atom is period 3 or lower. Okay, so we'll begin by redoing some of those examples that we looked at the beginning of the lesson, but this time following the steps. So I know you already know what the structure looks like, but let's follow the steps. So first we start by counting the valence electrons. There are 2 hydrogens, and each of them has 1 valence electron. So that's a total count of 2 valence electrons. We'll place the atoms on the page and start with a single bond between the atoms. Counting by twos as we go, that line represents 2 shared electrons. So we count to 2, we've already reached our total electrons, so there's no more electrons to put in the picture. That means no lone pairs. So we check stability, look at each hydrogen, and notice that each hydrogen has 2 electrons in total, including the shared pair. So the hydrogen on the left is stable, and then the hydrogen on the right is stable because of those 2 electrons. Okay, next example we did was Cl2. So start with your electron count. Chlorine's in group 17, 7 valence electrons each. So we're looking at 14 electrons in total. So we place the atoms on the page. There's only 2 of them. Side by side works. Moving on to step 3, a single bond between the atoms. Count by twos. That's 2 electrons. We need to get up to 14 electrons. So we've put 2 in the picture. Now I'll pick one of those outside atoms and put lone pairs until that atom is stable. Counting by 2. So I already have 2 in the picture from the single bond, so I just added 2 more, so that's 4, 6, 8. Once I hit 8 electrons around that chlorine, it's stable. I have to get up to 14, so I'm going to come over to the other side and continue to add electrons, counting by twos. 10, 12, 14. There we go. So all 14 electrons are in the picture. Now I check for stability. So looking at the chlorine on the left, I see 2, 4, 6 plus these shared is 8 electrons. Checking the chlorine on the right, 2, 4, 6 plus these 2 is 8. And so we continue. I realize we haven't had to make a multiple bond yet, but we'll keep going and eventually get there. Okay, CH4. Counting the valence electrons. You have 1 carbon, that's 4 electrons each, so there's 4 electrons from the carbon, and you have 4 hydrogens at 1 electron each. So there's another 4 electrons for a total of 8 electrons. Place the atoms on the page. Carbon has 4 electrons. It's going to need to make 4 more electrons to be stable. So it has a combining capacity of 4. It'll be the central atom because hydrogen, needing only 1 electron, has a combining capacity of 1. So we place the atoms on the page and start with our single bonds. Count by 2s. 2, 4, 6, 8. There we go. We've got all 8 electrons in the diagram. Now we check for stability. Each hydrogen is stable with the 2 electrons being shared, and this carbon has 2, 4, 6, 8 electrons. Perfect. Okay, moving on. After methane, we did water. Pause the video at any point and work ahead of me, and then listen in. Check back with the video when you think you're following the steps. So, counting valence electrons. There are 2 hydrogens, each with 1 valence electron each. So there's 2 electrons from the hydrogen, and 1 oxygen at 6 each. So a total here of 8 electrons. Position the oxygen in the middle because its combining capacity is 2, as opposed to hydrogen at 1. Oxygen needs 2 more electrons to be stable. Place the bonds, 2, 4. Now I look at lone pairs. Outside atoms first, please. That's the rule. Follow the rules. So hydrogen on the outside is already stable. Hydrogen on the left side is already stable. And so I come inside to the oxygen now to finish placing lone pairs. So we were already at 4 electrons, 6, 8. There we go. Is each atom stable? Well, the hydrogen's good with just 2 electrons, and the oxygen now 2, 4, 6, 8. Perfect. Moving on to oxygen, O2. All right, there's 2 atoms at 6 electrons each. That's 12 electrons in total. So we need 12 electrons in our diagram, our Lewis structure. So start with a single bond, 2. Now we go to an outside atom, 4, 6, 8. Go to the other oxygen, 10, 12. I must stop because I've reached the 12 electrons. But it's true that I notice that although the oxygen on the right is stable with 8 electrons, the one on the left is not. And here's where the step comes in, that now that one atom is not stable, we're going to reposition a lone pair, for example this one, from an atom that is stable, so the oxygen on the right, and we're going to reposition that as a multiple bond. Now check for stability. This oxygen here has 2, 4, 6, 8, perfect, and this oxygen 2, 4, 6, 8. Are there 12 electrons in the diagram? In total, 2, 4, 6, 8, 10, 12, perfect. So there's our final answer. Okay, try N2, nitrogen gas. 2 atoms of nitrogen at 5 electrons each takes us to 10 electrons. Place the atoms on the page and start with the electrons. 2, 4, 6, 8, 10 over here. I realize that nitrogen on the left isn't stable, so now I'm going to reposition electrons. When I do that, though, I realize that that nitrogen on the left is still not going to be stable. It only has, as we can see, 2, 4, 6 electrons. And so I'll need to reposition again from the atom that's already stable, that has the 8 electrons, and now we come up with that triple covalent bond that we've seen before. So final answer here, each atom is stable and there's 10 electrons total in the picture. Okay, so the challenge here is just to follow the steps in order. So I'm going to list a number of structures here for you to try. So after you've copied them down, pause the video and follow the steps. Okay, so you'll see these examples. There's 6 that are viewable now: CO2, NH3, CH3Cl, C2H4, the chlorate ion, the ammonium ion, and 3 more at the bottom: nitrate, bisulfate, and then iodine pentachloride, so ICl5. Okay, give those a shot, follow the rules, follow the steps in order, and then you can check back for the answers. Okay, I didn't go straight to the final answer. I thought I would show you the electron count and the placement of the atoms on the page for each example. So if you did get stuck with any of these, check your electron count and check the placement of the atoms on the page. Here's the bottom three. You'll notice here that I've placed the hydrogen off of one of the oxygens that's around the sulfur. So if you tried to put that H off bonding to the sulfur directly, the placement of the atoms is incorrect. So this hydrogen needs to be coming after one of these oxygens. Okay, so if you check this work, then if you don't, like if you see your error, you can try to fix it now and continue. Pause the video, finish the questions, and then check back. Okay, if you just want to see the final answers, perhaps you advance the video. I'm going to quickly speak through each of these in case someone needs to hear how it's done. So 2, 4, 6, 8, 10, 12, 14, 16. Both oxygens are stable, but the carbon is not, and so I'm going to reposition electrons, 2 from here and 2 from here, to maintain the symmetry. A lot of these molecules will have some symmetry to them, and there's our final answer for CO2. For ammonia, 2, 4, 6, hydrogens are all stable. I put the remaining lone pairs on the nitrogen. It's stable with 8. 2, 4, 6, 8, hydrogens all stable. 10, 12, 14. There's the 14 electrons, and carbon is stable. 2, 4, 6, 8, 10. I notice I need 12 electrons. The hydrogens are all stable, so I put that here on the carbon. And now I realize that the carbon on the left is not stable. So I'm going to reposition this lone pair as a double bond in between those two carbons. And a trick for you, for all the structures that we're drawing, carbon will never have lone pairs in the final answer. So keep that in mind. Chlorate, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There we go, square brackets and charge. The chlorine's stable with 8 electrons, and so is each oxygen. Ammonium, 2, 4, 6, 8. There's our 8 electrons, everything's stable, square brackets, positive charge. Nitrate. You see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's it. We've hit our 24 electrons. So now we'll reposition. You can pick any one of those oxygens in order to form the double bond. And then you'll just need your, your square brackets. Oops, changed color there. And we formed the Lewis structure for the nitrate ion. There should be a lone pair there. Okay, now which oxygen did you need to form that double bond at? Well, it really doesn't matter. The true structure is a blend of all 3 of these diagrams, which we refer to as resonance structures. So I'm quickly drawing that double bond into the 3 positions. You'll notice that each structure is stable with an octet around every atom. So you can draw any one of these on a test, but just so that you're aware, the nitrogen-oxygen bond length is actually identical in this ion, and all 3 of them are the same, and we just don't have a notation or a way of representing that bond, that nitrogen-oxygen bond that's somewhere in between that single or double bond. And so the true structure is a hybrid or a blend of all 3 of these structures. Okay, and finishing up with the bisulfate ion here, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. The hydrogen was already stable, 25th and 26th there. Now sulfur stable, square brackets, and the charge. And the last one, 2, 4, 6, 8, 10. 12, 14, 16, 18, 20, 22, 24, 26, 28. 30, 32, 34, 36, 38, 40, and 2 more, 42 electrons. It's okay, remember our exceptions to the octet rule, it's okay for the central atom here of iodine to go beyond the octet rule. You'll notice it has 12 electrons, and 10 or 12 is perfectly fine when the central atom is period 3 or lower. Okay, that's it.